Hi, this is Max Liu, and this is my Lab 2 motion of a falling object. So these are the things that we're going to be going over today. The purpose of this lab is to measure the motion of an object, a paper ball falling from rest. The observed data and the computational data will be compared, and then the two computational data we'll be using will be one factoring only gravity and another factoring gravity and drag. So here's a brief preview of the results. So as we can see here, the computational model that has gravity and drag better predicts the position, the observed position as time goes on, rather than the gravity-only model. The three fundamental principles are Newton's second law, gravitational force, and the next one will be drag. Newton's second law describes the relationship between the force acting on the object and the resultant motion of the object. Newton's second law is used to find the net force of the object, and then the momentum principle will be used to derive these formulas, the velocity update and then the position update formula. These equations will be used to calculate the position in the computational model later. The gravitational force on Earth formula will be used since the ball is falling towards the ground. The gravitational constant on Earth is 9.8 meters per second squared, and is represented as a lowercase g, shown here. The interactions with the particles in the air result in a drag force. The larger the surface area of the object, the larger the drag force. The drag force also needs to be accounted for because the object falls slowly and acts against gravity, as shown in the free body diagram. And then the equation here, B stands for the proportionality constant, and then the absolute value of velocity is speed squared, and then V hat is the direction of the velocity. So here's the video analysis. The system is the paper ball, and the surroundings is the Earth and the air. The initial conditions are the position being 0.175, velocity is at rest, so 0, and then the total time is 0.483 seconds. This is the Glossop code for gravity only. I set the ball's mass to 0.0045 kilogram, and then the initial position vector was set to the value shown in the previous slide, and then delta t was set to 0.017 since the video was recorded at 60 frames per second. The proportionality constant was set to 0 since gravity is the only force in the system, acting on the system. And then you have F net is over here is the force of gravity formula, and then I have then I update the ball's velocity and ball's position using the velocity update and position update formula. The code for gravity and drag are almost the same, except I changed the B constant to be 0.00456. This value was found by trial and error until I got a final position that was about the same as the observed position at t equals 0.483 seconds. And then to calculate net force, I use the drag force formula shown in the fundamental principle slides, and then I added it with the force of gravity to get F net, and then used the velocity update, position update formula again. Here are the results. The model that has the gravity and drag better predicts the position compared to the model with just gravity. So at t equals 2 seconds, the difference in the observed and the gravity and drag model appears to be the greatest, and the gravity only model shows the position at a further point at each time interval compared to the gravity and drag model. This is due to drag counteracting gravity, so the ball is falling at a slower rate, resulting in the position not being as large. And then some possible errors could be due to physical properties of the paper ball, which is rough instead of smooth, resulting in more drag, or the video not being completely still, causing error in the recording of the position. To address what does it mean, which models predict the terminal velocity. So terminal velocity happens when the force of drag pointing up has equally balanced the force of gravity pointing down. So the model that accurately predicts terminal velocity is the one on the right, the velocity versus time with gravity and drag. As you can see here, as time goes on, the graph flattens out, meaning that it's no longer increasing and that net force is equal to 0 due to drag and gravity being equal to each other. So for the what if, imagine the object was initially thrown downward. Would the terminal velocity in this case be the same or different from the case where the same object was initially dropped from rest? So the only thing I changed was I set the initial velocity to be -1, so to like simulate a ball being thrown instead of from rest. And the terminal velocity will still be the same because the terminal velocity is based on the magnitude of the drag force being equal to the magnitude of the gravity. So terminal velocity will just be reached sooner if thrown instead of from rest. In conclusion, the experiment was conducted to show the effects of drag and gravity on the paper ball. A tracker was used to record the position of the ball from rest, and a computational model were created based on gravity as well as gravity and drag, and then the models was then compared to the observed data in the real world.